Good evening to everyone. My name is Dr. Chirupreddy Venkateswara. Today, we are going to see Norton's theorem. So, in this Norton's theorem, what and all I am going to cover here means, who is invented Norton's theorem? What is the statement of Norton's theorem? And the current flowing through the load resistance has to find. For that, what are the steps we need to follow? Those things we are going to see. So, the Norton's theorem, the named after E.L. Norton, who developed it for the first time. So he is an engineer employed at Bell Laboratory, USA. So the Norton's theorem, the named after E.L. Norton, who developed it for the first time. So he is an engineer at Bell Laboratory, USA. So coming to the statement, it states that any two-terminal linear bilateral network containing a number of voltage sources and number of resistors can be replaced by an single equivalent circuit. That single equivalent circuit consisting of a current source in parallel with a Norton's resistance. So here the current source is the Norton current. So this is the pictorial representation of Norton's theorem. So if you observe this figure, so this rectangular box indicates that linear network with the number of voltage sources and number of resistors. So if you observe the statement, it states that the Norton's theorem states that any two-terminal linear bilateral network. So we are having two terminal. The first terminal is the A, another terminal is the B. So this is the linear bilateral network. So this linear bilateral network containing a number of voltage sources and number of resistors. So those number of voltage sources and those number of resistors can be replaced by an single equivalent circuit. So this is the single equivalent circuit. That single equivalent circuit consisting of a Norton's current in parallel with the Norton's resistance. So this is the statement of Norton's theorem. So where IN or ISC is the short circuit current supplied by a source. So this is also called as a Norton's current. So Rn is the equivalent resistance of the network as seen from the two terminals A and B. It is also called as Norton's resistance. So when you are calculating Norton's resistance, so we have to keep it all the sources, we have to make it all the sources are short circuited or replaced by the internal resistances. If we are having any current sources, those current sources are make it as a open circuits. So the next one is RL. RL is the load resistance. So what are the steps has to follow to obtain the load current or to draw the Norton's equivalent circuits? So let us consider a simple circuit and it is shown in below figure. So this is a simple circuit. So if you observe this circuit, it having one voltage sources and number of resistors as well as one load resistance. So here we consider one simple circuit. So that is shown here. So to find the current through the load resistance. So how much current is passing through this load resistance? So the following steps are has to follow. The step one is to determine the current through the load resistance. How much current is passing through this load resistance? So for that, temporarily remove the load resistance from the terminals A and B. So that is shown in below figure. So if you observe this figure, so they are removed the load resistance from the terminal A and B temporarily. So the second one, the second step is the determination of short circuit current over Norton's current. So to find short circuit current over Norton's current between the terminals A and B, so between the terminals A and B, so by keeping all the sources to their original position, that means whatever the sources they given, those sources should be there in the original position. We are not going to change anything here. As well as whatever the load resistance is there, that load resistance we can make it as a short circuit here. So that is shown in below figure. So if you observe here the load resistance we are make it as a short circuit. So now we need to calculate how much current is passing. That is short circuit current. We can call it as a Norton's current. So if you observe this figure, R2 and R3 are connected in parallel. So now the resistance is R2 into R3 divided by R2 plus R3. So why R2 into R3 divided by R2 plus R3? Because here R2 and R3 are connected in parallel. So now the circuit is, so whatever the resultant resistance we are getting, that is in series with the resistance R1. So in this figure, R1 and R2, R3 divided by R2 plus R3 are connected in series. Then the total resistance is equal to R1 plus R2, R3 divided by R2 plus R3. So now the circuit is, so these two resistors replaced with this total resistance. So now the circuit is V as well as the total resistance they given. So if you observe this figure, so here we know the V value as well as we know the total resistance. So from that we are going to identify the total current. So according to the Ohm's law, I equal to V by R. So now we know the total resistance R, that is, so V by R1 plus R2 into R3 divided by R2 plus R3. So this is the current. So because of the source voltage, how much current is passing here, that we know. So this is the total current I. So this total current is passing through the load resistance. So up to here. So once it is reached to this node, so the total current is splitting into two ways. Some amount of the current is passing through the R3 as well as some amount of the current is passing through the R2. So now we are going to identify how much current is passing through the R2. So whatever the current is passing through the R2, that is the short circuit current. So now the short circuit current ISC over Norton's current IN is ISC over IN equal to, according to the current division rule, the total current into opposite resistance. So here we are calculating the current, how much current is passing. So for this resistance, who is the opposite resistance? R3. R3 divided by, so R3 plus R2. The total current into opposite resistance by sum of the resistances. So for example, so we need to calculate how much current is passing through the R3 means. So for this, who is the opposite resistance? R2. R2 divided by R2 plus R3. So during this time, whenever the current is passing through the R3, but we required how much current is passing through the R2. That is the short circuit current or Norton's current. I into opposite resistance R3 divided by R3 plus R2. So now we know the Norton's current. So the step 3, we are going to determine Norton's resistance. So in order to find the Norton's equivalent resistance of the network, so as seen from the terminals A and B, so that is shown in below figure. So when you are calculating the Norton's equivalent resistance of the network, so if any voltage sources are there, those voltage sources we can make it as a short circuit or replaced by the internal resistances. If any current sources are there, those current sources we can make it as a open circuit. So now the circuit is, so in the original circuit they given only one voltage source. So as per this statement, so if any voltage sources are there, those we can make it as a short circuit. So based on that, so in the original circuit they given one voltage source, that voltage source we can make it as a short circuit. So if you observe this figure, in this figure the R1 and R3 are connected in parallel. So in the above figure, R1 and R3 are in parallel. So now the resistance is R1 into R3 divided by R1 plus R2. So these two resistances are replaced by the R1 into R3 divided by R1 plus R3 because these two are connected in parallel. So now the circuit is, so this is the circuit. So this one is connected here, R1. So this is the R2. So now we know the equivalent resistance, that is R1, R3 divided by R1 plus R3. So this resistance is connected in series with the R2. This is the R2 value. So in the above figure, if we observe that, so this R2 and R1, R3 divided by R1 plus R3 are connected in series. These two are connected in series. So now the resistance is, that means the Norton's resistance is, so R2 plus R1, R3 divided by R1 plus, sorry. So here, if you observe this figure, R2 and R1, R3 divided by R1 plus R3 are in series. Now the Norton's equivalent resistance is R2 plus R1 into R3 divided by R1 plus R3 because these two are connected in series. So this is the Norton's equivalent resistance. So if you observe here, so when you are calculating the Thevenin's resistance, that means the Thevenin equivalent resistance, so as well as when you are calculating the Norton's equivalent resistance, so both are same. The same steps you are following here in order to obtain the Norton's equivalent resistance. So now we know the short circuit current or Norton's current now, as well as we know the Norton's resistance. So once if you know the Norton's resistance as well as the Norton's current, so from that we can draw the equivalent circuit. How we are going to draw the equivalent circuit means by replacing the entire network. That means whatever the network they given, that network replaced with the short circuit current or Norton's current in parallel with the Norton's resistance. So that is shown in below figure. So if you observe the figure here, so they replace it with the entire circuit with Norton's current in parallel with the Norton's resistance. So in step 5, initially we remove the load resistance from the AB terminal. So what we are doing here means whatever the load resistance we removed from the AB terminal, that load resistance we are connecting back to its original position. That means wherever we removed the load resistance, so there we are going to connect. So that means the terminal A and B we are connecting back here. So that is shown in below figure. So the load resistance we are connecting back to AB terminals. So in step 6, to determine how much current is passing through the load resistance. So here, if you observe here, again the current division rule will place here. So by applying current division rule, so we need how much current passing through the load resistance. That is IL equal to, so the total current into, here the total current is the Norton's current. Here the total current is the Norton's current into, so what is the opposite resistance for this RL? Rn divided by Rn plus RL. This is the how much current is passing through the load resistance. That is IL equal to the total current, that is IN into opposite resistance Rn divided by Rn plus RL. This is the load current. So now we know the load current. So as well as they given the load resistance. Once if we know the load current as well as the load resistance, so we are going to obtain what is the voltage drop here. So in step 7, the potential difference across the load, that is VL equal to IL into RL. So now we know IL value. So that is VL equal to, our IL value is IN into Rn divided by Rn plus RL. So this is the load current into the load resistance, that is they represented. So this is the voltage drop across the load resistance. So this is about the Norton's theorem. So upcoming video, we are going to see the problems of Norton's theorem. Thank you. Thank you so much.